taking a more interdisciplinary approach to providing solutions on food waste, for example, in terms of the Rio +20 follow-up. Looking more into the public health dimension when we reconcile what are known as the Millennium Development Goals with the Sustainable Development Goals, which is a process which is ongoing in New York, and clearly tackling more the most vulnerable populations and probably needing to focus more on parts of sub-Saharan Africa. So overall conclusion, clearly, this is very much on the agenda of the international community. A lot is being done. Clearly, we need more coordination and more synergies. We use the concept of policy coherence for development. We need to also assure coherence of policies, whether agricultural policy with research policy, with environmental policy, and even with health policy. Coherence amongst policies is the order of the day, and this is something which we as European Union will continue profiling. And clearly, better targeting of development aid. The European Union is a major donor, but we need to become more effective and more visible in terms of targeting aid, and clearly agriculture and food security is something which we will give a priority for the 2014-2020 programming period. Thank you very much for your attention.
I suggest that we would take comments and questions at the end after having listened to all three speakers, and proceed now to welcome Professor David Strachan, who will be talking to us about genomes, environment, and public health, the end of the beginning or the beginning of the end.
Well, thank you. This week is the 70th anniversary of the Battle of El Alamein, which was an Allied victory in which the courage and determination of the people of Malta played a major role. And on the 10th of November 1942, Winston Churchill announced to the British nation, this is not the end of the war, this is not even the beginning of the end, but it may be the end of the beginning. So that's the title I've chosen for this review of where perhaps the new technologies in genomics have got us. Have they got us to the end of the beginning or the beginning of the end? There's an awful lot of money has flowed into new diagnostic technologies, the omic technologies over the last 4 or 5 years, and so much so that the really important omics is the Department of Economics. And you might feel that all that money has been spent, we deserve victory, we must get a product at the end. And what I want to try and do is to give you some impression of how far we may have got after all that money has been spent, and whether we should continue spending more. And I want to do that around a framework which some of you will be familiar with from the writings of the American epidemiologist Rothman, who advanced this idea of necessary sufficient component concept of causation, where if you take a complex disease, and I'm going to use as an example asthma because it's my own field of research, a complex, heterogeneous, multifactorial disease, it looks just like these Maltese spring flowers. There's a variety out there, and we might sort of simplistically dissect that out into 3 types of disease, each of which has their own combination of causes which are collectively necessary and sufficient. So up in Gozo we have atopic, or what used to be called extrinsic asthma, and that shares one component, the A component, with the larger non-atopic or intrinsic asthma on the main island of Malta. And then we might have some unusual types of asthma on Camino, where I understand there's only about 4 residents. And that, in turn, shares one component, which is the F component, with the larger non-atopic intrinsic asthma. So they're just very simplistically trying to give you some concept of a complex multifactorial disease. And where do these components come from? Well, if we go right back to the very beginning, I'm not sure that the Neolithic people would have recognized genetics, but they probably would have recognized that disease runs in families. And about the time that Winston Churchill was entering politics in the UK, this little pedigree diagram appeared in the British Medical Journal. That's all you had to do to get yourself into the British Medical Journal in 1909, is to write a short letter. So asthma runs in families, and it was claimed at that point that it was a dominant inheritance disease. We now know it's much more complicated than that. And the other strand of evidence comes from studies of twins. We think of identical twins as identical as two peas in a pod, but actually it's interesting that if we look at identical twins, they are not identical. If you have a co-twin with asthma, your chances of having asthma are about 50%. So the beginning of the beginning is all about individual risk. Some people develop asthma and allergies and some don't. Asthma and allergies run in families. Identical twins are certainly more commonly concordant than non-identical twins, as they are for most diseases, but asthma is not unique in that identical twins have discordance. And in fact, the concordance rate in identical twins for asthma is at the top end of the range. If you look at other diseases that are thought to have a genetic predisposition, often the concordance rates are way below 10% in identical twins. And that leads to the idea that possession of genes are not necessary for asthma and not sufficient. We need to think about genes in combination with other factors. And we also need to think about the penetrance, in other words, the chance of developing the disease once you actually have the genetic variants that are important. And that's, of course, despite substantial shared non-genetic factors in twins. So coming back to Rothman, we've got this very simplistic diagram. We're trying to build up these pies. Once we have the complete pie, disease occurs. So what other cofactors might be important along with genetic predisposition? Well, Maltese people have been influenced from Europe, from the north, first by the original European Union, the Imperial Roman Empire, and they were probably very familiar with dampness when they reached the northern island of Britannia. Must have been a pretty miserable existence with no woolen clothing. And then, of course, the Maltese have been influenced from Africa, the Arab influence, and just to illustrate occupational exposures and the so-called non-farming lifestyle, which has become of interest as a risk factor for asthma. And then, of course, more recently, the current European Union has become very taxed with the idea of air quality, both indoors and outdoors, and the way in that it affects respiratory disease. So we've got a number of environmental factors which are known to associate with a disease such as asthma, and we have to integrate those with the genetics that is emerging. And, of course, no history of Malta would be complete without the Knights of St. John, the Knights Hospitaller, who, as we learnt in the opening ceremony, brought state-of-the-art biomedicine to these islands. And the biomedicine contains two important components. There's the therapeutics, and there's something about biological mechanism. And with asthma, there's been an awful lot of interest in biological mechanism over recent years, and there's been a hope that if we could integrate the genetics with the biomedical knowledge, we might be able to advance both individual prediction, personalized medicine, and our understanding of disease mechanisms. But to do so, of course, we have to inject some new technology. So where best to look than British Isles and to introduce what I'm sure Winston Churchill would have been very proud that London buses have been exported to these islands. In fact, the new technology that's been influential in genomics has been some very powerful biochemistry and nanotechnology, which allows you to test up to 1 million different genetic variants simultaneously on something the size of a microscope slide, which is conventionally called a chip. And the recipe for a genome-wide association study tended to be, well, you applied for enough money to test these chips on about 1,000 cases of a disease and 1,000 controls. And what you got out of that was something that is shown here as a plot of the log-transformed p-values against the chromosomes across the genome, and the higher the peak, the more significant the association. And that's generally called a Manhattan plot, although I think the Manhattan residents will be a bit disappointed with this one, which is rather typical for a first stab, 1,000 cases, 1,000 controls, one genome-wide significant hit. So I think it's more like a Maltese skyline than a Manhattan skyline. But what happens, of course, is that people then use more cases and more controls, and I've been involved with the Gabriel Asthma Consortium, which has brought together 10,000 cases and slightly more controls, and you begin to see, as the numbers increase, the numbers of peaks start increasing. And the world is divided into two groups of people, those who get excited by all this potential biological mechanism and those who don't. But I think it's difficult not to feel that there's something when you actually look at the skyline from our latest collaboration in asthma genetics, which is 25,000 cases and nearly 100,000 controls. It's very clear now where the main statistically significant associations lie. And this looks very much like the London skyline from our departmental coffee room, where the Shard, which is now the highest building in Europe, dominates and probably is about twice the height of any of the other tall buildings in London. Well, what does all that genomics tell us about the aggregation in families, the individual risk, and the biological mechanism? Well, if we take those most well-established loci that associate with asthma risk in these genome-wide association studies and put them together into a genetic risk score, we can put a receiver operating characteristic curve together so that on the vertical axis, this is how many asthmatic children you would pick up, and on the horizontal axis, how many of the normal non-asthmatic children you'd have to find in order to detect your asthmatic children. And you can see that this ROC curve varies rather subtly from the line of identity. They're certainly not up in the top left-hand corner, which is what you want for a diagnostic test. So, for instance, to detect about a third of the asthmatic children, you have to test between 20 and 25% of the population. This is not individual prediction of the sort that was promised. So the individual prediction is not giving us the tool that we need to predict asthma in families. It doesn't explain why twins are concordant. It doesn't provide us with much opportunity for personalized medicine. The peaks that have been identified do contain some which were predicted from known biological mechanisms, but it also intriguingly points, probably at least half the peaks point to new biological mechanisms, which we hadn't even thought of. So if we think about the end of the end, why do some people develop asthma allergies and some do not? We're actually rather disappointed at the power of genetic variation as it's currently measured to predict not just asthma risk, but a whole range of other common diseases have been poorly predicted at the individual level, poorly predicted in families, so there's this phenomenon it's called missing heritability. But what I want to do is, we're public health people here, we're not interested so much in the individuals, we're interested in the population. And something which is missing from those Manhattan plots is an estimate of the size of the effect. We would normally expect an epidemiological paper to write about the magnitude of effect rather than just its significance. So I want to pursue that idea in relation to this diagram, which may be familiar to those who followed the writings of Geoffrey Rose, that you could have a burden of disease represented by the heavy shading there, which could either be due to a small risk widely spread in the population or a large risk that's concentrated amongst a minority. Well, population attributable risks are of some concern when we deal with comparisons between populations because they rely not only on relative risks but also on the prevalence of exposure. But actually in genetic work, the frequencies of these genetic variants are often quite similar across European ancestry populations. They often assume that the association is causal, although I don't particularly wish to pursue that in detail at the moment. I think what's interesting is that this concept of population attributable risk applies to the locus, the region of the genome, rather than the individual SNPs that might have been measured. And finally, people get worried because you can't add these population attributable fractions up to 100%. And I would say that's perfectly true, but you can add them up to 100% provided you take account of interactions. I'll come back to the interactions in a moment, but let's just look at how population attributable risk operates with that stupendously large peak on chromosome 17, the Shard peak, which is now well recognized as a correlate of childhood asthma and wheezy bronchitis. So here we have a Rose-type diagram looking at that particularly common variant. But of course, that same 27% of the disease could be due to a smaller group in the population who either have a rare variant in that region or who have a combination of a genetic and an environmental stimulus. And that's the interest that there might be a subgroup effect. Well, what's really striking is if we apply this concept across the genome for asthma, as we've done in just the last few weeks for a British 1958 birth cohort, which has been followed from birth through to middle age, and which has been one of the components of the large study, we find that that large peak on chromosome 17 accounts on its own for 19% of that lifetime risk of asthma, and rather more of childhood asthma, as I showed. And if you put all the genome-wide significant loci together from this latest consortium, the Transnational Asthma Genetics Consortium, we're now accounting for 83%, or at a minimum, maybe somewhere around 74, 75%. This is a very large burden of disease that is already accounted for. So we're back to our Rothman plot here, and just to put into the context of those figures I just showed for the genetics, here are some guesstimates, and you'll have to allow me the luxury of just presenting these because a longer presentation will be necessary to present the detail. These are the sort of population attributable fractions that we might have in the UK context for the various other factors that are associated with asthma. Well, there's something wrong, isn't there? Because those environmental paths are adding up to quite a lot, and then you've got a biomedical path on the right-hand side, which is perhaps a third, perhaps as half of all asthma is something to do with allergic sensitization, and then on the left-hand side, we've got 75% or more attributable to these genes that have just been discovered. Well, of course, the reconciliation of that is that if genes and these non-genetic factors are interacting together, in other words, they form components of these pies, then we can immediately see how you can have a disease which is almost 100% genetic and 100% environmental.